Hey there! This video covers how you can find sums of higher powers of roots without the use of formulae specific to those powers of roots. However, you do need to know the more base level formulae, so if you don't know how we get those notations, I'd suggest you check the first video of this chapter. Or, if you're not aware of how we get these formulae, check out the second video. Now, assuming you've got everything before this down, we can move on to what's next in our list. We already know the formulae up to alpha cubed, but now, what if we go to the next step up? Your first instinct could be to create another formula for it, and although that could work, it would also imply you needing to create formulae for every single power of roots moving forward. Now, I don't know about you, but I absolutely hate having to memorize a crap ton of formulae just to solve that one little obscure question that could or could not be given in a test. Rather, I'm more of a fan of keeping a handful of formulae to heart and deriving my way through. I just feel it helps me be more adaptable. With that said, fortunately, we do have a technique taught in this chapter. But before we get to alpha to the power of 4, I'd like to show you how we can use this technique for the sum of alpha squared itself, and then we'll build up on it. Let's have a random quadratic polynomial, ax squared plus bx plus c equals 0. This means it only has the two roots alpha and beta. This would imply that if x is replaced with alpha or beta, the whole polynomial should result in 0. After all, they are the roots, right? So what happens if we do replace x with alpha and beta? Well, nothing actually. We just get two of the same equations, just in terms of alpha and beta respectively. But what if we add these two equations themselves? To avoid clutter, I'll be grouping the terms together in the same step. What you end up with is an equation with each term being added and grouped up like this. Now, if you take a look at each resulting term, I'm sure you'll notice that this is actually the expanded form of the sum of alpha, and this is the expanded form of sum of alpha squared, which means this is the sum of alpha to the power of 0 for quadratic equations. This would mean that you can represent a polynomial itself in terms of the sums of various powers of its roots. But of course, it's kind of an eyesore to both see and write them in sigma notation every single time, which is where we get introduced to the S notation. Sum of alpha is represented as S1, sum of alpha squared is represented as S2, and sum of alpha to the power of 0 is represented as S0. Keep in mind that this is sum of alpha squared and not sum of alpha whole squared. Assuming that the question provides you with the values of the coefficients, once you get this equation, you can now substitute S1 with minus b by a and evaluate S2 using normal algebra. The exact same thing applies to the sum of alpha cubed, or S3, as well. Replace x with each of the roots and create a set of equations. Add the equations and group them up according to the coefficients. Rewrite the expanded forms with their respective S notations and solve away using formulae you already know. Now, if you've noticed by now, the equation we got using our S notation is exactly the same as our original polynomial, just x replaced with s. And because of that, for the next few derivatives, I'll be skipping this part of the process and directly jump to the S notational equation. Which finally brings us back to the quartic equations. Given that we have a general quartic polynomial, we can replace the x's with our S notations like so. Then, we can easily figure out the S4 by replacing the other terms with their respective formulae and solving accordingly. It's that easy. But of course, with any easier process, it comes with its caveats. And I'm sure you've noticed it by now, that there's a limit to how many formulae we can substitute it with. This will be more obvious for a pentic equation. If we try to do the same thing for a pentic equation, we end up with an S notation like this. Sure, we can replace S0 through S3 with their respective formulae, but what about this S4 term? We can't use what we figure out from the quartic equation because, well, that's a completely different equation. And naturally, we don't know any formula for this either. What do now? Basically, S5 becomes impossible to resolve without knowing what S4 is for this equation. Lucky for us, there is a trick that can help us figure this out. Take our original polynomial. What happens if we divide the entire equation with x? We end up with the same equation, but the powers of all the terms are reduced by 1. Now, if you treat this as its own equation, you should be able to realize that you can replace this with the S notation like this as well. Thus, We have an equation where the highest is S4 and the lowest is S of minus 1. Now you can figure out S4 using your known formulae. As far as S of minus 1 is concerned, if you recall the pattern we figured out in the last video, the formula over here should be sum of alpha, beta, gamma, delta divided by sum of alpha, beta, gamma, delta, epsilon. Why do we have 5 roots in the denominator despite this having an S4 as its highest? That would be because our original polynomial was a pentic equation and not a quartic one. Correction. It would be more accurate to say that you need to use the formula that utilizes the version of the polynomial where the lowest power of x was 0. Now simply replace the sigmas with the coefficients using their formulae and solve for S4 algebraically. Hey there, quick intermission. If you're confused as to how I substituted the coefficients for S of minus 1, it boils down to the basic formulae of sums of polynomials. For any general polynomial of arbitrary degree, sum of alpha is minus b by a, sum of alpha beta is c by a, sum of alpha beta gamma is minus d by a, sum of alpha beta gamma delta is e by a, and so on and so forth. Basically, if it's the sum of products of odd numbers of roots, you have a minus sign. If it's an even number of roots, there's a plus sign. And if you have the product of a certain number of roots, the numerator is of the next numberth alphabet of the English language. Meaning, sum of alpha, a single root, you have b as the numerator, which is the second alphabet. Sum of alpha beta, the product of 2 roots, the numerator is the third alphabet, c. And in this way, we got the sum of product of 4 roots to be e by a, and the sum of product of 5 roots to be minus f by a. Carry on. And so, in this way, now that you've evaluated S4, you can move on to figure out S5 from our original polynomial. Simply use the equation written in the S notation, plug in the value for S4 that you've calculated, and voila! There you have it. Now go, run along and figure out S6 or S7 or any sum that tickles your fancy. Or you could hit the brakes, think about it a little, and do a double take at me and ask, now hold on there, Miji-sensei. That can't be all there is to it, because I recall you also giving us a formula of the sum of alpha cubed, but for quadratics instead. Surely you're not going to tell us that there's no method for solving that, are you? To which I would answer... You're quite right, and the method for solving that is the same as the method we used to solve the previous problem. A general quadratic equation in its S-notational form might be this, but similar to how we divided the entire polynomial with x to bring the powers down, here we'll do the complete opposite and multiply the equation with x, giving us an S-notation like this. Moving on, you can simply plug the values for S2 and S1 for the formulae you know and automatically solve it. In this way, you keep going to higher and higher powers, finding S4, S5, and even S10 for mere quadratic equations. You can keep going higher and higher. Just do keep in mind that you will not be able to solve for higher power sums directly without solving for the one before it. So yeah, best of luck. But it doesn't even stop there. Because with this technique, you can actually go downwards even further. The only thing you need to keep in mind is by what power of x you divide the equation by. Let's say you want to figure out the sum of alpha to the power of minus 2. Or in other words, s of minus 2. While your first instinct might be to look at the highest power of x, figure out the difference to minus 2, which is 4, and divide the entire equation with x to the power of 4. But that way, you'll have end up with an s of minus 3 and an s of minus 4 term as well. Remember, similar to how you needed to know the value of all other s terms when figuring out S5, you'll also need to divide this equation so that s of minus 2 is your only unknown. So instead of looking at the highest power, you'll have to look at the lowest available power, which is 0. And thus, you end up with an equation like this, and all else is history. And with that, you basically armed yourself with the techniques to figure out the sum of any power of roots of any degree polynomial. The main takeaway from this video is that just about any polynomial can be represented in terms of the sums of its roots using the S notation, and also that you can adjust the same S notational equation by dividing or multiplying the whole thing with powers of x, or as a shortcut, s. Now unfortunately, this video has already gone on for long enough, so we do not have time for examples. There's way too many variations for me to cover. What I'd recommend you to do is rewatch this video as many times as needed and practice whatever sums are in your particular books. If there are any examples you'd like for me to cover, feel free to link them down in the comments below, and hopefully I'll manage to find some time to put them in their own separate video. And with that, we can finally move on to the final part of this chapter, figuring out sums of roots of completely different polynomials by using a given polynomial, so long as a small small relationship between the roots have been presented to us. But that, of course, will have to be taken care of in the next video. Thanks for watching and peace out.